Hi folks, we're talking about circles here in geometry, and one of the first things we like to talk about when we talk about circles in geometry is tangents. And remember, a tangent is nothing more than a line that touches our circle in only one point. That point where my line touches the circle has a name. It's called the point of tangency. Okay, so there are two. I did it again. I did this today in class too. Tangency. I keep leaving out my N. T-A-N-G-E-N-C-Y. Okay, so there's the point of tangency. Two big properties of tangents that we need to be able to use. So let's just look at those. First one is this. The tangent, any tangent, is always perpendicular to. This means perpendicular to. So really that's redundant, perpendicular to, but perpendicular to the radius at the point of tangency. The at the point of tangency really just kind of makes sense because it's not like a tangent, or any line for that matter, could be perpendicular to something it doesn't touch. So in other words, it's not perpendicular to that radius because it doesn't even touch it. It's perpendicular to the radius that touches it. In other words, the radius that comes to that point of tangency. And remember, the definition of a radius is it's a segment that has one endpoint as the center of the circle and the other endpoint is on the circle. So the endpoint of the radius we're talking about that's on the circle would be the same as the point of tangency. So here's my radius. Here's the endpoint that's the center of the circle. Here's the endpoint on the circle. It is the point of tangency for my tangent line, and that's always going to be a right angle. Always, always, always. And that ends up being very important because anytime you have a right angle, that becomes more than just that information. And the reason why is if you have a right angle, then you can have right triangles, which means Pythagorean theorem, which means special right triangles might apply, which means trig functions, sine, cosine, tangent. So anytime you have a right angle, it can be sort of a gateway to knowing a lot more information. So that's a very important piece of information. Also, one thing I want to point out there is, let's say I have one of these. I have a tangent somewhere. Let's say this tangent comes down here and it touches the circle in one point and only one point. And let's say it's tangent to the radius, which it is, at the point of tangency. So that means this is a right angle. What if I do that? Well, now I have a right triangle. But the thing I wanted to point out about this is, remember that let me rephrase this already before I've said it. The whole definition of a circle is about the radius. A circle is the set of all points that are an equal distance away from a single point that we call the center. So let's say my equal distance is 3 centimeters. That means I can go 3 centimeters in any direction, and there's my circle. And the 3 centimeters in any direction is my radius. So the radius is a common distance. All these points are the same distance away from the center. So what that means is every radius is exactly the same length. The radius is always going to be the same length. And of course there are infinitely many radii. Radii is the plural of radius. So if I draw more than one radius, which I can draw 500 radii if I want to. I could draw any radius I want to draw. They're all going to have the same length. So if I have this situation right here, and I keep moving out of the screen, sorry about that. If I have this situation right here, and if I knew that, for instance, the radius had a length of 3 meters, 3 inches, doesn't really matter. Then that means I also know over here that this portion has a length of 3, right here. So from here to here. And remember, if you see a number written as a length of a segment, it's usually centered on the part of the segment it's talking about. So if I have a 3 written like this, it's not telling me the whole thing is 3. It's telling me this part is 3. Okay, so keep that in mind. Let's use that. One of the ways in which we are asked to use that sometimes is to be asked, and this kind of seems a little counterintuitive, so I wanted to do some of these. We'll be asked if we have a radius. For instance, here, the problem would probably say, is AB, not if we have a radius, if we have a tangent. The problem would say, is segment AB tangent to circle C? And you can't say, yeah, it looks tangent, so that's it. No, we have to have a mathematical reason that it's tangent. Well, if it is a tangent, then that means it should be perpendicular to the radius, which means this should be a right angle. So what we're going to do is we're going to check and see if the Pythagorean theorem works for these distances. Because remember, the Pythagorean theorem converse, or the Pythagorean converse, says if one side squared plus the other side squared equals the third side squared, then it must be a right triangle. So that would mean that yes, this is a right angle, and yes, AB is a tangent. So that's what you're being asked to do here. You're confirming that AB is a tangent. We're going to do that by checking to see if this is a right angle. So I'm going to do 5 squared plus 12 squared equals, remember the hypotenuse is always across from the right angle, not touching it. What's this total distance? It's 5 plus 8, which is 13. So 13 squared. A little sort of side note here. For some reason, students rarely have trouble saying, oh yes, that's 13. I would add those together. But the same students who rarely have trouble with that very often have trouble. Let's say you have this, something similar. I'm going to call this QR. If I have to find the length of segment QR, a lot of students, for whatever reason, would look at that and say, oh, it's 6x. No, we don't multiply to get the total length. I did not do 5 times 8, I did 5 plus 8. So if I want this total length of QR, the total length of QR is x plus 6. So keep that in mind. If we want to find the length of a segment from the parts, we're adding the parts, not multiplying the parts. Okay, so back up here, we have to decide whether or not this is true. So 25 plus 144, that's 169. Is 13 squared 169? Yes. So yes, that means that is a right triangle, and yes, that means that AB is a tangent. Okay, same thing here. Slightly different looking. Notice that they told me that this is the whole distance. So this time I don't have to add anything. I've got legs squared, 7. Remember, you do have to think about where would the right angle be. If AB is a tangent, the right angle would have to be right there at the point of tangency. So you have to think about this is where we're thinking it must be in order to make this a tangent segment. So we need to know that to know which ones are the legs. So the 7 and the 24 would be the legs. The other thing we could use to tell us what the legs are, if it's a right triangle, is knowing that the hypotenuse would have to be the longest. So 25 is bigger than 7 and 24, so that would have to be the hypotenuse. And this is going to work out. 7 squared plus 24 squared is indeed 25 squared. So yes, segment AB is a tangent. Okay, not segment BC. BC intersects the circle. Your tangent cannot intersect the circle. Okay, the other property of tangents I wanted to point out to you is that if you have two different tangents, so here's one, here's the other, from the same external or exterior point, and in this case my point is called N, then they are congruent. I like to refer to this as the ice cream cone theorem, because if you look at this, it's a little bit like an ice cream cone, and it makes sense that if you have an ice cream cone, the two sides of the cone have to be the same height, or else your piece of ice cream is going to fall off. Your chunk, your sphere of ice cream is going to fall off the cone. So I think of this as the ice cream cone theorem. Okay? It's not the official name. But the point is, if I have a point outside my circle, and I draw a tangent from that point to the circle, and then I draw another one, it would have to be on the other side of the circle, those two segments are going to have the same length. Segment AB is going to have the same length as segment AC. Okay, so let's see what we can do with that. Here's an example of something we could do with that. Here's my exterior point. AB is a tangent, AD is a tangent, so therefore these two pieces, these two segments have to be the same length. So I would say 7x minus 2 equals 3x plus 8, and solve. So subtract 3x from both sides, add 2 to both sides, and I get x equals 5/2. I took 10/4 and I simplified it. Okay? Same thing on this one. I'm just setting the two sides equal to each other. 7x plus 4 equals 3x plus 68, and then solving. Now I'm not going to do that one though, because sometimes you will find that you will have one instead. I'm going to go ahead and use this picture, and I'm going to put different measures here because I want to show you this other type. Sometimes you'll have one that's more like this, and it may or may not have parentheses, but let me show you what's special about this one. Okay, so 3x times x plus 2 is the length of AB, and 2 minus 3x is the length of AD. Well, just like above there, we know we have to set these equal. So 3x times x plus 2 equals 2 minus 3x. Well, when I do my distributive property here, I'm going to get an x squared. When you have an x squared, you have a quadratic equation. So this is now solving in a quadratic equation. We set it up the same way. We put one of them equal to the other because they're both tangents from the same point, so they must be equal. It's the fact that we got a certain type of equation after that that makes this a little different. We're still just solving whatever equation we got. We just happen to get a quadratic equation. So we have to dust off our quadratic equation solving skills and do that. The first thing we generally want to do to solve a quadratic is move everything to one side. So I'm going to go ahead and add 3x to both sides. And I think this problem actually may not work out the way I meant for it to. I'm pretty darn sure it will not. I kind of wanted to give you one that was factorable. Remember that we have several different ways we can solve a quadratic. We can factor it. We can use the quadratic formula. We can complete the square. We could potentially graph it. The ones we use most commonly really are factoring and quadratic formula. Generally, I factor if I can, and if I cannot factor, I use the quadratic formula. This one I can't factor. If I multiply 3 times -2, that gives me -6. And if I'm looking for two numbers that multiply to give me -6 and add to give me 9, I'm not going to find those numbers. They don't exist. That's not factorable. So if it's not factorable, I would have to use the quadratic formula, which looks like this. The A in this case is 3, B is 9, and C is -2. This one's going to be kind of messy, so I'm not even going to do it. But I just wanted to point that out, well, it's not that messy, but that's what happens if you get a quadratic, is you have to use those quadratic equation solving skills rather than just freaking out and running away. One last little thing I want to point out to you. Ice cream cone theorem. Again, the two sides are congruent. Look what happens if I put my circle inside a triangle. Basically, I have 3 different ice cream cones. Pretend this is more symmetric than it really is. In other words, these two are the same, these two are the same, and these two are the same. So that's something to keep in mind. We're going to explore a little bit more later. This would happen if I took any type of polygon. Let's pretend that touches, and put it around my circle. Okay, these two segments would be the same, these two segments would be the same, these two the same, and these two the same. And that's about it for this.